Java development tooling JDT in Eclipse. Now we are considering Java development tooling JTD. Java development tools JTD plugins extend the platform workbench by providing specialized features for editing, viewing, compiling, debugging, and running the Java code. Here you can see Java elements, how these elements are represented in the package view. The package org.eclipse.jdt co-defines classes that models the element that compose a Java program. JDT uses an in-memory object model to represent the structure of a program. This structure is derived from the project's class path. The model is hierarchical. Elements of a program can be decomposed into child element. Manipulating Java element is similar to manipulating resource object. When you work with the Java element, you are actually working with the handle to some underlying model object. You must use the exist protocol to determine whether the element is actually presented in the workspace. Here you can see iJava model represent the root Java element corresponding to the workspace, the parent of all projects with the Java nature. It also gives you access to the projects without the Java nature. iJava project represent the project in the workspace, child of iJava model. Compilation unit represent the Java source.java file, child of iPackage fragment. iPackage fragment use represent a set of package fragments that maps the fragments to an underlying resource with which either a folder, jar, or zip file, child of iJava project. iPackage fragment represent a portion of a workspace that correspond to an entire package or an portion of the package, child of iPackage fragment root. All Java elements support iJava element. Some of the elements are shown in this package view. These elements implement iopenable interface, since they must be opened before they can be navigated. The figure here shows how these elements are represented in the package view. The Java elements that implements iopenable are created primarily from the information found in the underlying resource files. The same elements are represented generally in resource navigator view. This is package explorer. Here you can see iJava model root, then iJava project. Here compilation unit, iPackage fragment root. Here jar, iPackage fragments. Since 3.3, here you can see Java elements, a Java compilation unit, and a content outliner that displays the source element in compilation unit. Since 3.3, iopenables that are the root of itypes implement itype root. These are iCompilation unit and iClass file. Other elements correspond to the items that make up the Java compilation unit. Figure here shows the Java compilation unit and a content outliner that displays the source element in the compilation unit. These elements implement iResource reference interface, since they can provide corresponding source files. As these elements are selected in the content outliner, their corresponding source code is shown in the Java editor. Here you can see iPackage declaration. Represent a package declaration in a compilation unit, child of I compilation unit. Here I import declaration represent the single package import declaration, child of I import container. Here you can see I type represent either a source type inside the compilation unit or binary type inside the class file. Here you can see I field represent a field inside the type, child of I type. Here you can see I method represent a method or constructor inside the type, child of I type. Here you can see I package declaration. I import declarations, and here I type, here I field, and here I methods. Now here you can see key connections between JDT and Eclipse platform. The JDT is implemented by a group of plugins with the user interface in a UI plugin and non-UI infrastructure in a separate core plugin. This separation of UI and non-UI code allows the JDT core infrastructure to be used in GUI less configuration of the Eclipse platform and by other GUI tools that incorporate Java capabilities but do not need JDT UI. This illustrates the key connections between JDT and the platform. Here you can see perspectives, views, editors, wizards, action sets, property pages, and reference pages are in the workbench. Here Java perspective package, just view, Java editor, wizards for new Java, action set, Java action set, property pages for Java build and the Java source attachment, and Java persistent pages are inside JDT UI. Here project natures, builders, marker, and marker types are inside workspace. Here Java project nature and Java builder and Java problems are inside JDT core. Java perspective, type hierarchy perspective is connected to perspectives, plug into perspectives. Packages view, type hierarchy view are connected to views. Java editor, scrapbook editor are connected to editors. Wizard for new Java project, package, class, interface. Wizard for new Java project, package, class, interface, scrapbook page are connected to wizards. Java action set, create Java project, package, class, interface, scrapbook page, open type in editor is connected to action sets. Property pages for Java build path and Java source attachment are connected to property pages. Java preference pages, Java class path, variables, code formatter, Java editor, organize imports are connected to preference pages. Here you can see project natures, builders, and marker types are connected to inside workspace. Java project nature, Java builder, and Java problem are inside JDT core. Java project nature is connected to project natures, Java builder is connected to builders, Java problem is connected to marker types. Now we are considering Java elements and their resources in JDT core in JDT plugin developer guide. The following code snippet shows how to get the Java element from their corresponding resources. Many of the Java element correspond to generic resources in the workspace. When you want to create the Java element from generic resource, the class Java core is the best starting point. The following code snippet shows how to get Java element from their corresponding resources. The class Java core, the plugin runtime class for the Java model plugin containing the core UI free support for Java projects. This is in the package org.eclipse.jdt.core. Once you have a Java element, you can use the JDT API to traverse and query the model. You may also query the non-Java resources contained in a Java element. The project is not configured for Java, has no Java nature. Get the package fragment or package fragment root. Get a .java compilation unit .class file or .java package fragmented root. Get the non-Java resource contained in my project. Now we are considering opening Java editor in Java UI utilities in JDT UI. The following snippet shows how Java UI can be used to open a Java editor and display a specific member. The class Java UI, the central access point for Java UI plugin ID id org.eclipse.jdt.ui. This class provides statics method for creating various kind of selection dialogues to present a collection of Java element to the user and let them make a selection. Opening a Java editor on a compilation unit. This is in the package org.eclipse.jdt.ui. The methods open in editor and reveal in editor also work for class files and members contained in class files. Now we are considering launching a compiled Java program. Running Java program in JDT debug. Java programs that have been compiled in a Java project can be run by getting the appropriate IVM runner for the Java project and they're running the class by name. The following code snippet shows how the class my class inside my Java project can be launched. The interface IVM runner, a VM runner starts a Java VM running a Java program. This is in the package org.eclipse.jdt.launching. Another way to launch a Java program is to create a Java application launch configuration. launch it. The following code example shows how my class inside my Java project can be launched using a simple launch configuration. By default, the resulting running application uses JRE and the class path associated with my Java project. Now we are considering observing JUnit test run in JTD JUnit integration. The JDT JUnit plugins let you to listen to test runs. To observe test runs, register your listener with JDT core.add test run listener. The method public static void add test run listener. Listener adds a listener to test runs. This is in the class JUnit core, and this is in the package org.eclipse.jdt.junit. This listener will report all sessions and test cases started. Now we are considering adding annotation processes in APT in Eclipse in getting started in JDT annotation processing. You can add annotation processes to your project under Java, then compiler, then annotation processing, then factory path. Processes can be contained in a jar file or Eclipse plugins. The factory path list include both Java 5 and Java 6 processes. Now we are considering API reference. For example, we can consider package org.eclipse.ant.launching provides support for ant launching. Now we are considering extension points reference. For example, we can consider org.eclipse.jdt.apt.core.annotation processing factory. Plugins which contribute JSR 175 annotation process should extend this extension point in order to participate in compilation. Now we are considering JDT overview map of JDT plugins in other reference information. This table is useful for determining which plugins a given plugin should include as prerequisites. The Eclipse Java development tooling provides a comprehensive Java development environment. The Java development tooling itself is divided up into a number of separate plugins. The following table shows which API packages are found in which plugins as of Eclipse 4.18. This table is useful for determining which this table is useful for determining which plugins in the given plugin should include as prerequisites. Here you can see com.sound.jdei and org.eclipse.jdei, org.eclipse.jdt.debug, and required plugin ID is org.eclipse.jdt debug. Here org.eclipse.jdt.debug.ui. The required plugin is org.eclipse.jdt.debug.ui. org.eclipse.apg packet org.eclipse.jdt.co. Required plugin ID org.eclipse.jdt.co. API package org.eclipse.jdt.annotation. Required plugin is the same with the same name. Here API package com.sun.mirror.asterisk and org.eclipse.jdt.apt.co.asterisk. Required plugin org.eclipse.jdt.apt.co. Here the API package org.eclipse.jdt.launching. Required plugin org.eclipse.jdt.launching. Here API package org.eclipse.jdt.co.manipulation, org.eclipse.jdt.co.refactoring, and required plugin org.eclipse.jdt.co.manipulation. Here API package org.eclipse.jdt.ui. Here required plugin org.eclipse.jdt.ui. API package org.eclipse.jdt.junit, required plugin org.eclipse.jdt.junit and org.eclipse.jdt.junit.co. Here API package junit.asterisk and org.junit.junit and required plugin org.junit. API package org.eclipse.jdt.launching and required plugin org.eclipse.ant.launching. Here API package org.eclipse.ant.ui.launching and required plugin org.eclipse.ant.ui. Now we are considering Eclipse JDT 4.26 plugin migration guide in migrating to Eclipse JDT 4.26 from 4.25 in plugin migration guide. One of the goals of Eclipse 4.26 was to move Eclipse forward while remaining compatible with previous versions to the greatest extent possible. That is, plugins written against the Eclipse 4.25 API should continue to work in 4.26 in spite of the API changes. The key kinds of compatibility are API contract compatibility and binary compatibility. The API contract compatibility means that valid use of 4.25 APIs remaining valid, and for 4.26 there is no need to revisit working code. Binary compatibility means that the API method signatures etc. do not change in the ways that would cause existing compiled binary code to no longer link and run with the new 4.26 libraries. As an exception example, we can consider class format exception. Class format exception thrown by a class file reader when encountering an error in decoding information content in a .class file. This is in the package org.eclipse.jdt.co.util. Now this is the end of my presentation. Thank you very much for watching it.